welcome to this video on some topics in topology. Here we are going to discuss the concept of filter in topology. So what's meant by a filter? A filter on a set X, a filter which is defined on a set X is a non-empty collection F or it's script F, a non-empty collection script F. So it stands for script F stands for collection of sets, collection of subsets of X. So a non-empty collection script F of subsets of X. And each of these subsets are also non-empty. So a non-empty collection of non-empty subsets of X are taken in script F, which satisfies the following conditions. And these conditions are satisfied by the elements of F. The first condition is it's an intersection. This condition is on intersection that says that finite intersection of members of F are also in F. Let's see if F1 and F2 are two elements of F, two members of F2, or two collections which are present in F, in script F, then the intersection F1 intersection F2 is also a member. And if F is a member of script F and there is a superset which contains F, suppose G is a superset, that superset is taken here equal to G. If G contains F, and then G must also be present in the script F in the collection. So what does it mean? Therefore, see, the second condition means says that it's closed under supersets. So the first condition says that the set is the collection is closed under taking intersection of finite intersection of elements members, and the second condition says that it's also closed under the operation of taking super sets. Okay. Then we need now some examples. So of course we want examples. So first example, it's a straightforward example. It is given here. Let X be a topological space and let X be a point in X. X be a topological space and small x be a point in X. Then UX, that is script UX, it is the complete neighborhood system of XC. Remember about that. Think about the complete neighborhood system of the point X which is present in the topological space X. Then it can act as it can make a filter. So you can verify the two conditions are satisfied by this complete neighborhood system of a given point which is present in the topological space X. Indeed, this is probably the prototype of C. You can see that you can from the history of the definition or the development of the concept of the filter. See, it's a fact that it acts as the prototype. Which one? That is the complete neighborhood system. The complete neighborhood system acts as the prototype for the concept filter that is discussed here. That means filter. The concept of filter actually developed from the concept of complete neighborhood system, or it is derived from, or it is developed by generalizing the concept of the complete neighborhood system at a point X. So the filter UX, the filter which is produced by UX is so often it's called the neighborhood filter at X. So it's called the neighborhood system, the neighborhood filter. So this particular filter is called the neighborhood filter at the point X. Next we have to discuss another definition. We have another definition that that tells us about the filter base. So what's meant by the filter base? A filter base on a set X. A filter base on a set X is a non-empty collection C. A non-empty collection C of non-empty subsets of X. It's a non-empty collection script C of non-empty subsets of X such that if U1 and U1 and U2 they from use the from the notations used here, it is clear. Yeah, you can think that it is open sets. So both are open sets. So U1 and U2 for the subsets U1 and U2 elements of C, and there exists a third element in C in the same collection. If in the collection there exists U1 and U2, there exists a third element, subset in that collection, such that U3 is a subset of U1 intersection U2. So what condition is satisfied here? U3, the third subset is third set is a subset of the intersection of U1 and U2. Next, immediately we have a lemma which is related to this filter base and the concept of filter. So it is it links both concepts. Okay. What does the lemma say? Let C be a filter base on a set X. Let C be a filter base of a set X on a set X. Then the collection F, which is defined by collection F, such that F is a subset of X. F is a subset of X. Script F equal to the collection of sets where F is a subset of X, such that there is U in C. There exists U in C with the property that U is a subset of F. There exists whenever there is an element in X. See, whenever F is a subset of X. See, whenever F is a subset of X, then whenever there is a subset of X, then there exists a U in C. An open set, then there exists a subset in C, in the collection C, such that U is subset of F. So whenever this happens, and whenever there exists such a set F, then that F can be taken in script F. In this collection, those subsets of X which have this property. So whenever or there exists a subset in C or member in C, such that that member is a subset of F. That kind of F can be considered for inclusion in the definition of this set script F. See, then if that kind of collection is taken, then that collection will be a filter. So if this way we define, if we can define F, and then F will be a filter, the script F will be then a filter, and F is called in this case F is called the filter generated by the filter base C. So since there exists the filter base C that that generates the filter, that is the reason for the existence of the filter F. So it can be called the filter generated by C. So we are now going to see how to prove this lemma. See, one thing is very clear, that the set F, the script F is closed under supernets, under the operation of taking supernets. So it is clear that F is closed under the operation of taking supernets. Why? Because it's because if F is if F is an element of F. See, suppose that F is an element of the script F, and then there exists the U in C, such that U is a subset of F. And so whenever G is a superset of F, whenever you take G which is a subset of X, and it's a superset of F, and then the same U will also be present, since U is a subset of F, and so the same U is enough to say that it is a subset of G also. So G can also be a member of script F. So therefore that says that whenever F is a subset of G, then G is also a member of F, and this says that F is closed under supersets, under the operation of taking supersets. Okay, or consideration under the consideration of taking supersets. Next, suppose that there are two members of F. We suppose we are taking two members of F1 and F2. So what remains to show now? It remains that intersection, the finite intersection of any two members is also a member of the same set. So for that we take we consider choose two elements, f1 and f2 be two elements of f, and as we choose f1 and f2 elements of f, then the definition says that the definition of f says that there exists u1 and u2. Corresponding to f1 there must exist u1, and corresponding to f2 there must exist u2, where in C there must exist these two subsets such that u1 is a subset of f1 and u2 is a subset of f2. Okay. Since C is a filter base, and also since C is a filter base and there is an element u3 in C, since C is a filter base, there's an element u3 in C such that u3 is a subset of u1 intersection u2. Okay, keeping that in mind, and that condition or that property in mind, keeping this fact in mind, we can proceed. Now, when we consider the intersection of f1 and f2, f1 and f2, you take the intersection of f1 and f2, then it is clear that u3 is a subset of f1 and f2, and this set u3 is present in f, and therefore f1 intersection f2 must also be present in f, and hence f is a filter. So the first condition is also satisfied, hence it's a filter. Okay, thank you.